Okay, can you see my screen and the presentation, the first page of the presentation?
Yes.
Perfectly. First, I should thank the organizers for this nice possibility to talk about my old colleague and I think my close friend Maxim, and I would like to support him in such a not difficult year as we all have now. My talk will be concentrating formally concentrated around our cooperation with Maxim for the last 40 years. And for the first slide, I will give precisely the formal list of our joint papers. Our cooperations goes and went beyond, far beyond this for, while interesting for me, I hope for Maxim as well, papers. And in my talk, I would like to briefly expose what is the spirit of our cooperation, what is the spirit of Maxim's contribution, big contribution to the theory we are considering in such publications, and what is typical and specific for his very deep contribution. First of all, let me remind a little bit the context of our research as it was started practically 40 years ago. In 1983, Dubrovin and Novikov published a paper when they have proposed a natural formalism for an interesting class of quasi-linear partial differential equations, which are very typical in many applications. But for a very particular class, his Hamiltonian formalism turned out to be the adequate one. Formally, I will speak about only the one-dimensional case, because especially this case is very, very deep and fruitful in our joint publications with Maxim. So the first system of equation with arbitrary number, finite number of unknown functions of two variables, one space and one time variable t, with the matrix V depending on the variables U, is typical in many applications. The Dubrovin and Novikov contribution was not the first in studying Hamiltonian structures of such systems. It was a classical topic to derive, for example, Hamiltonian structures of all Lagrangian structures for fluid equations and gas dynamic equations. But usually people before that time derived such Hamiltonian structures from Lie algebras and Lie groups. Especially Arnold's contribution was very interesting. But Dubrovin and Novikov, unexpectedly for many, provided a deep and simple connection to very standard Riemannian geometrical entities, namely metric G and Christoffel coefficients gamma. Namely, it was possible for them to represent some integrable, as we know now, class of equations of type 1 within the Hamiltonian form with Poisson bracket, Hamiltonian H, and first order Hamiltonian operator. It turned out, and they proved it, that for the non-degenerate case, for non-degenerate metric G, the Hamiltonian structure is very interestingly providing a flat metric G, and every flat metric will provide a system of hydrodynamic type which has a Hamiltonian structure. That was unexpected in some sense. Turned out to be not very difficult. Nowadays we can consider it's a standard result, but at that time it was really unexpected. And after that, Novikov proposed a very interesting problem for me. Namely, suppose that a Hamiltonian type system, HTS, meaning Hamiltonian type system, of Dubrovin-Novikov Hamiltonian type, suppose it has a complete set of Riemann invariants, meaning that it's diagonalizable with some transformation of the field coordinates U to some U bar. Such a transformation is very typical in many applications of hydrodynamic type systems, and many classical papers of 19th and 20th century are studying such systems. And Novikov just conjectured that combination of such two facts, that system has Dubrovin-Novikov type Hamiltonian structure 2, and diagonalizability provides a automatic integrability. And important examples of such system which were known for some decades were Witham system and Benny system, reducible by many methods, for example, with Zakharov method through a hydrodynamic type one-dimensional system. So it's very easy to prove that if we have Riemann invariant U bar, then the flat metric in such a coordinate system U bar is also diagonal. Then, since it's flat, this coordinate system produces an orthogonal curvilinear coordinate system in a flat Euclidean, or in many cases pseudo-Euclidean space. So it turned out in next 1 or 2 years that it was a real, very deep and unexpected branch of classical differential geometry related to orthogonal curvilinear coordinate systems, which was really not reinvented, it was really reinvested and gave a big profit to the theory of integrable nonlinear PDEs of that epoch, of the 80s and 90s, or in the 20th century. It was a forgotten world, really, at that time, because everyone knew about orthogonal coordinate systems, say in R2 being polar coordinates or elliptic coordinates, in R3 being spherical coordinates, cylindrical coordinates, conical coordinates, or elliptical coordinates. But that was basically, that's all. They are not very deeply considered. They are just useful in mathematical physics, not more. There was no understanding at that time of this forgotten world of classical differential geometry, which studied such coordinate systems, orthogonal curvilinear coordinate systems in flat space. It was really a big fun for me and for many of my colleagues at that epoch to dig out very interesting, unexpected links between classical papers by Gaston Darboux, Ribocourt, Combiscure, in French mathematical school of the end of the 19th century. Luigi Bianchi, certainly we know his name, but he also wrote very, very deep papers on curvilinear orthogonal coordinate systems. By a student by Darboux, Georgi Tsitseka, who was subsequently a founding father of Romanian mathematical school, and very deep results obtained by Tsitseka was very astonishing for the community of integrability of nonlinear PDEs in the 90s. Certainly Luther Eisenhardt from American Mathematical School. And it turned out that Dmitry Fedorovich Egorov, who was in fact one of the founding fathers of the Moscow mathematical schools in the beginning of the 20th century, also contributed quite a lot in the theory of specific and very important for applications now, today's applications of orthogonal curvilinear coordinate systems. And many other people did this, and I just mentioned such few names for results which are now directly invested into modern theory of hydrodynamic type integral systems. Good. So that was 40 years ago a first and very interesting link of integrability of hydrodynamic type systems and classical differential geometry. But what about effective formulas? If you look into the deep and interesting and very maybe unexpected result by the classical people like Darboux, Bianchi, Eisenhardt, and Egorov, we will see a lot of formulas which are practically reproducible in the language of hydrodynamic type systems. But what about effective formulas for solutions of hydrodynamic type systems? Like, say, we have solitonic formulas for KdV equation and other formulas for finite zone solutions for the quasi-periodic and quasi-periodic KdV solutions. Unfortunately, at that time, 40 years ago, or maybe 35 years ago, we knew and we understood that it's easy to reduce the problem of integrability of quasi-linear hydrodynamic type system to the system of overdetermined linear system of PDEs for conservation laws, infinitely many conservation laws, or commuting flows, infinitely many of them, for an integrable diagonalizable Hamiltonian type system. But unfortunately, formally, the answer given by generalized hodograph method was not that much effective. Such methods, classical and very interesting and mathematically astonishing, did not result in equally simple, explicit formulas for solutions. And that was precisely the stage where Maxim Pavlov came into play. Well, formally or informally. I will not mention about many other contributions of our other colleagues, by Boris Dubrovin, by Krichever. Unfortunately, both of them passed away from us, from the previous generation of Novikov's mathematical school, and Mokhov, Oleg Mokhov, and others, Zhenya Ferapontov. I will just concentrate on what was the contribution of Maxim into this unexpected world of classical differential geometric methods. Let me start with the first our joint publication. That was publication in 1991. Sorry, I only have a Russian language version published in Russian Mathematical Surveys, and I suspect it was not translated into English, but the main it's a short note, 2-page note, which describes an explicit, more or less explicit formula for finding conservation laws and commuting flows for the system 1, which is the system of Zakharov-Beny. After a few very maybe not so easy steps, and we proceeded to a very interesting formula 4, which is somewhat unexpected for me, but Maxim was the guy who was the right way to obtain good, simple, and non-trivial formulas. It is typical for him 30 years ago and nowadays, I think so. So after a few steps, we obtain, I would say, explicit formulas for that, and we publish this note. And after that, what happens next? In some 10 years, the idea, which was just briefly mentioned in this short note, namely relation of the method of integration to the so-called Yegorov coordinate system, resulted in the next publication, which was published 12 years afterwards. And we studied in more detail, I would say exhaustively, maybe Maxim will correct me, even in 20 years after that publication, we still are at the same stage of understanding of Yegorov type, hydrodynamic type systems. We studied deeply hydrodynamic type system 1, which are the same, which are diagonalizable, and has a very interesting physical property, which is a very natural one. Suppose that system 1, sorry, any questions? Okay, suppose system 1 has a non-trivial but physically meaningful symmetry. For example, it's invariant with respect, say Galilei or maybe Lorentz transformation. It's natural for a physical system to have such a symmetry, point symmetry. And after that, that was known already 10 years before this paper in 1991, I guess, or a little before, in one of my publications, I have shown, following closely the papers by Dmitry Yegorov, that precisely systems of hydrodynamic type which have Galilean or Lorentz symmetries, they necessarily have a special property of being not only Hamiltonian, but only two Hamiltonian, or even in many physical cases, which are also meaningful, three Hamiltonian structure, which is very typical, by the way, for integrable system, but, well, this should be done for hydrodynamic type system. And it was done, and in this paper we studied a lot what can be drawn precisely to the to the best of our knowledge, what can be drawn from this hypothesis. If hydrodynamic type system is of Dubrovin-Novikov type, is diagonalizable and has a physical symmetry of Galilei transformation, or maybe Lorentz transformation. Good. After that, our next two papers, which were again in 10 years, unfortunately, formal publications come in with step on almost 10 years. And I would say that between such days, we did a lot of cooperation, meaning exchanging ideas with Maxim and our colleagues in United Kingdom, in Moscow, in other respects, not only on hydrodynamic type and etc. But it turned out that the results by Maxim especially are very fruitful in studying not only nonlinear PDEs, but also nonlinear ordinary differential equations. Namely, if we will study a mechanical system, which is, well, looking very trivial. Suppose we have a mechanical system with a Hamiltonian given here. So we have one space coordinate x, one time coordinate t, and certainly one momentum p related to x with a standard Poisson and Hamiltonian structure. But suppose that the potential depends on t. It's very typical in many mechanical systems, and many classical papers of the 19th century and 20th century were devoted to studying such system in effort to understand whether they are at least Liouville integrable. So it's a system of ODEs, not PDEs. It's just system of two nonlinear ODEs, and it turned out that our expertise in the theory of hydrodynamic type system provided us with the possibility to find a lot of closed form potentials V, where we can say that such a system is explicitly Liouville integrable. And I shall confess explicitly and honestly that that was Maxim who did the most of computations for us, because that understanding of spirit of computation, meaning analytical transformation with pure brain work, is very typical for Maxim, and it's really very unexpected for me in some respects. Because nowadays we are, at least at that time, and for many mathematicians even nowadays, we rely on either mathematical computer algebra software like Maple, for example, or any other software for computation, and we are omitting a lot in deeper insight into formula world. But Maxim, using computer algebra, still can do the brain work and extract real meaning of some cases when without his understanding it would be impossible to solve this problem, finding set of potentials V such that we have Liouville integrable systems. And a bit afterwards, since we study ODEs, it's a very classical and tempting and very challenging problem of understanding, say, for example, suppose we have a surface, a two-dimensional surface, curvilinear surface, in the usually flat Euclidean space. And classical people like Jacobi, Euler, and others tried and integrated a lot of, or Kovalevsky, for example, integrated a lot of similar systems describing geodesic flows on such surfaces. And it turned out that using, again, hydrodynamic type systems, or at least spirit of hydrodynamic type systems, ideas from the theory of hydrodynamic type systems, Maxim Pavlov, and that was definitely his contribution into this publication. Well, very recent for me, 2015. I almost quitted this nice but very, very, very challenging world of explicit integration of hydrodynamic type system by that time, by 2015. But Maxim was very insisting, very motivated, and very, I would say, apt and able to produce such a results which I believe are still unprecedentedly deep in the theory of two-dimensional integral geodesic flows. So formally speaking, I would say that unfortunately I do not proceed further in this direction, and maybe our colleagues today will give a deeper insight into modern world of integrable system and give tribute to Maxim to his 60th anniversary. That's my part of this tribute, and thank you very much, Maxim, for this long 40 years old cooperation. And I hope you will proceed further into this nice world of integrable systems. Thank you.